Okay, hi guys. So we'll be continuing on seeing more on the modes of representation of gas constants of equilibrium, rather equilibrium constants, not gas constants. So we'll be continuing on seeing that. So first example is, let's say we have AgCl. So AgCl in solid form gets dissociated into Ag plus aqueous and Cl minus aqueous. Okay, and another reaction we have in which Ag plus and 2NH3 aqueous forms a complex again aqueous. So let's say this was Kc1 and this the equilibrium constant was Kc1, and for this reaction it was Kc2. And if we see at the overall reaction, so at overall reaction we can just combine the two equations to get something like HCl plus 2NH3 aqueous forms Ag NH3 plus 2 whole twice plus NH3 whole twice plus and Cl minus aqueous. So let's say the equilibrium constant for this was Kc. So we can easily say that Kc would be equals to Kc1 into Kc2. This we also saw in the previous lecture, wherein we actually found out first the Kc1 and Kc2 of both the reactions, and then on multiplying we found that we got Kc of the resultant reaction. Okay, so let's now discuss about the units of equilibrium constants. So we have for Kp, Kc or Kpc also, we can have units depending on the concentration or partial pressure of the products divided by reactants. So some of the units may remain there, but if we talk about Kp naught, Kc naught or Kpc naught, so they are as per thermodynamics, hence they don't have units, because these quantities are as per thermodynamics. Okay, now let's discuss more on temperature. Okay, so the value of equilibrium constant is actually dependent on temperature. We'll shortly see why. Value of equilibrium constant is dependent on temperature. Okay, and for endothermic reactions we can write that the value of K equilibrium increases as the value of temperature increases. So as temperature increases, the value of K equivalent also increases. Okay, because endothermic reaction by the name itself suggests that reaction will move forward by absorbing more heat, or should the reactants need more heat to be getting converted into products. So if we are giving the reactants more heat, or in other words we are increasing temperature, the K equivalent would increase. And for exothermic reactions, we can write that the value of K equivalent decreases as the value of temperature increases. So as temperature increases, K equivalent decreases. Okay, why is this the case in case of exothermic reactions? Because if you look at K equivalent for exothermic reactions, again it would be concentration of products divided by concentration of reactants, and we know that exothermic reaction takes place via giving out heat to the atmosphere or releasing energy. Okay, so that is defined by having that is defined by in the name of exothermic reactions. But on the other hand, if we are increasing temperature, then more and more reactants would be getting produced and less products would be getting, more and more reactants would be not getting converted into products, or in other words, less products would be getting converted from reactants on increasing the temperature for an exothermic reaction. So due to which the concentration of products will decrease and concentration of reactants will increase. As a result, K equivalent would decrease as the denominator is increasing. So now let us look at what is heat. So let's define two subcategories of heat, Q, which is QP, which is nothing but heat exchange at constant pressure, where we can write that QP could be equal to delta H, okay, and QC would be heat exchange at constant volume. Where we can write QV as delta E. Okay, so or we can also write delta E or delta U. Okay, and delta H is, so H is enthalpy here, so delta H would be change in enthalpy, and similarly U is internal energy here, so delta U would be change in internal energy. Okay, so now for an let us define some endothermic reaction with the help of an example. So for endothermic reaction, we can write that heat is absorbed in chemical reaction or in this type of reaction. Okay, and some example can be 2A reacting with, or rather directly dissociating into B gaseous plus C gaseous, and delta H is actually required, which is x kilojoule per mole. X is some positive integer, or we can write that 2 molecules of, or 2 moles of gaseous A get some energy which is x moles of energy, x kilojoule of energy, and converted into Bg plus Cg. Okay, and for exothermic reactions, for example, so for exothermic reactions, heat is released in this type of reaction. Heat is released in this type of reaction. Okay, and example can be Again, let's say xg plus yg getting converted into cg or zg, and delta H in this case would be minus a kilojoule per mole. A is some positive integer. Okay, or in other words, we can say that A by the bond which is formed by having Z as the product releases some energy A in the product side. Hence, we can also write A in the RHS or in the product side. So with this, we come to the end of this lecture. In the next lecture, we'll be continuing on seeing more theory on endothermic and exothermic reactions. Till then, good luck and goodbye.